Current electricity. Concept of current. Current is defined as the rate of flow of charge. It is a scalar quantity. I is equals to Q by T. Unit of current. The SI unit of current is ampere, symbol A. 1 ampere can be defined as the current which flows in a conductor when 1 coulomb of charge passes through it in 1 second. I is equals to Q by T. Electric potential at a point. The potential at a point is defined as the amount of work done per unit charge in bringing a positive charge from infinity to that point. It is denoted by the symbol V. It is scalar quantity. V is equals to W by Q. Unit of electric potential. The SI unit of electric potential is volt. Symbol V. The potential at a point is said to be 1 volt when 1 joule of work is done in bringing 1 coulomb charge from infinity to that point. V is equals to W by Q, that is joule per coulomb, is referred as volt. Concept of potential difference. Example of water. Example of accumulated charges. Potential and potential difference. Potential difference between 2 points is work done in moving a unit charge from one point to other in electric field. Potential difference is equals to work done upon charge. Vpq is equals to Wpq upon Q, that is equals to Wp minus Wq upon Q. SI unit is 1 volt and 1 volt is equals to 1 joule per coulomb. Potential difference. The potential difference between 2 points is equal to the work done per unit charge in moving a positive test charge from one point to another. It is a scalar quantity. Va minus Vb is equals to W by Q. Unit of potential difference. The SI unit of potential difference is volt, symbol V. The potential difference between 2 points is said to be 1 volt if the work done in moving 1 coulomb charge from one point to the other is 1 joule. 1 volt is equals to 1 joule per coulomb. Concept of resistance. Definition. The obstruction offered to the flow of current by the conductor or wire is called its resistance. Cause of resistance. The resistance of a conductor depends on the number of collisions suffered by the electrons with the positive ions while moving from one end to another end. Factors affecting the resistance of a conductor. The material of conductor. The resistance of a conductor depends upon its material. Substances which have a large concentration of electrons offer less resistance, therefore they are called good conductors of electricity. On the other hand, substances such as rubber, glass, wood, etc., which have a negligible concentration of free electrons offer very high resistance, so they are called insulators of electricity. The length of conductor. A longer conductor offers more resistance. Resistance is directly proportional to length. The thickness of conductor. A thick conductor offers less resistance. Resistance is inversely proportional to area. The temperature of conductor. The resistance of conductor increases with an increase in its temperature. Resistance is directly proportional to temperature. Examples of electrical conductors. Silver, gold, copper, steel, seawater. Examples of electrical insulators: rubber, glass, oil, diamond, dry wood. Wire S is smaller than wire T here, thus wire T is longer, therefore it will have higher resistance. Unit of resistance. Unit of R is equals to unit of V upon unit of A, that is volt upon ampere, often referred as ohm. The resistance of a conductor is said to be 1 ohm if 1 ampere current flows through it when a potential difference of 1 volt is applied across the end of the conductor, that is 1 ohm is equals to 1 volt upon 1 ampere. Ohm's law. According to Ohm's law, the current flowing in a conductor is directly proportional to the potential difference applied across its end, provided that the physical conditions and the temperature of conductor remains constant. V is equals to IR. V by I is constant. Limitation of Ohm's law. Ohm's law is obeyed when only the temperature of the conductor remains constant. Experimental verification of Ohm's law. Here, there are various voltage across the resistors and the current in the circuit, and a graph is being plotted. Slope of VI graph. The slope of the straight line graph gives resistance of the conductor or wire. That is, delta V upon delta I is equals to R, or resistance of the conductor. IV graph. Slope of IV graph. The slope of IV graph is delta I upon delta V, which is the reciprocal of resistance of the conductor and is called the conductivity of the conductor. It is denoted by sigma and its unit is Simon per meter. Ohmic and non-ohmic resistors. Ohmic resistors, it obeys Ohm's law, that is, V by I is constant for all values of V or I. Non-ohmic resistor, it does not obey Ohm's law, that is, V by I is or the same for all values of V or I. Ohmic resistor, the graph for potential difference V versus current I is a straight line passing through the origin. Non-ohmic resistor, the graph of the potential difference V versus current I is not a straight line but is a curve which may not pass through the origin. Ohmic resistor, the slope of VI graph is same at all values of V or I at a given temperature. Non-ohmic resistor, the slope of VI graph is different at different values of V or I even at a given temperature. Example of ohmic resistors, all metallic conductors such as silver, iron, copper, nichrome, electrolyte with suitable electrodes, etc. Non-ohmic resistors, example, junction diode, LED, transistor, filament of bulb, etc. Specific resistance or resistivity. Specific resistance of a material is the resistance of a wire of that material of unit length and unit area of cross section. Unit of specific resistance. The unit of specific resistance is ohm meter. Factors affecting the specific resistance. The specific resistance of a substance is its characteristic property. It is different for different substances. It is very low for metals and alloys, that is around 10 to the power minus 8 ohm meter. Low for semiconductors, that is 10 to the power minus 5 ohm meter, but very high for insulators, that is 10 to the power 13 ohm meter. The specific resistance of a substance depends upon its temperature. It increases with the increase in temperature for metals, but it decreases with the increase in temperature for semiconductors. For some alloys, example, constant in manganese, it remains practically constant with change in temperature. Choice of material of a wire. The wire used for electric connections and for power transmissions. They are made of materials such as copper or aluminium whose specific resistance is very small. The resistance wire or standard resistors. They are made from alloys such as manganese, constantin, etc., for which the specific resistance is high. Fuse wire. It is made from an alloy of lead and tin. The filaments of an electric bulb. A tungsten wire is used because it has a high melting point. The heating element in appliances such as heater, toaster, oven, etc. A nichrome wire is used because specific resistance of nichrome is high. Superconductor. Definition. A superconductor is a substance of zero resistance or infinite conductance at a very low temperature. Example of superconductors: mercury below 4.2 Kelvin, lead below 7.25 Kelvin, niobium below 9.2 Kelvin. Electromotive force or EMF of a cell. Definition. The EMF of a cell is defined as the energy spent or the work done per unit charge in taking a positive test charge around the complete circuit of the cell, that is, in the circuit outside the cell as well as in the electrolyte inside the cell. Epsilon is equals to W upon Q. Factors affecting the EMF of a cell. The EMF of a cell depends upon the material of the electrodes, the electrolyte used of the cell. Thus, the EMF of a cell is its characteristic property. It is different for different kinds of cell. For example, the EMF of a voltaic cell is 1.08 volt. That for a Leclanché cell is 1.5 volt and a Daniell cell is 1.08 volt. Terminal voltage of a cell. Definition. The terminal voltage of a cell is defined as the work done per unit charge in carrying a positive charge around the circuit connected across the terminals of the cell. V is equals to W upon Q, voltage drop in a cell. Definition. The work done per unit charge in carrying the test positive charge to the electrolyte is called the voltage drop in the cell. V is equals to W upon Q. Relationship between EMF and terminal voltage of the cell. Epsilon is equals to capital V plus small v, or capital V potential is equals to epsilon minus voltage drop in the cell. Distinction between EMF and terminal voltage of the cell. EMF of the cell. It is measured by the amount of work done per unit charge in moving a positive charge in the complete circuit inside and outside the cell. It is a characteristic of the cell, that is, it does not depend on the amount of current drawn from the cell. It is equal to the terminal voltage when cell is not in use, while greater than the terminal voltage when the cell is in use. Terminal voltage of cell. It is measured by the amount of work done per unit charge in moving a positive test charge in the circuit outside the cell. It depends on the amount of current drawn from the cell. More the current drawn from the cell, less is the terminal voltage. It is equal to the EMF of the cell when the cell is not in use, while less than the EMF when the cell is in use. Internal resistance of a cell. The resistance offered by electrolyte inside the cell to the flow of current is called the internal resistance of cell. V is equals to I into small r. Here is the representation of a cell with its internal resistance. Relationship between EMF, terminal voltage and internal cell. Small r is equals to small v upon I, that is equals to epsilon minus capital V upon I, that is equals to epsilon minus capital V upon capital R, that is equals to epsilon upon capital B minus 1 whole r. Factors affecting the internal resistance of a cell. The surface area of electrodes. Larger the surface area of electrodes, less is the internal resistance. The distance between electrodes. More the distance between the electrodes, greater is the internal resistance. The nature and concentration of electrolyte. Higher the concentration of electrolyte, greater is the internal resistance. The temperature of the electrolyte. Higher the temperature of electrolyte, less is the internal resistance. Combination of resistors in series. Rs is equals to R1 plus R2 plus R3. Combination of resistors in parallel. 1 by R is equals to 1 by R1 plus 1 by R2 plus 1 by R3. Measurement of electrical energy. W equals to QV equals to VIT is equals to I square RT is equals to V square T by R. SI unit of electrical energy. The SI unit of electrical energy is Joule. Electrical power and its expression. Electrical power P is equals to W by T equals to V I is equals to V square upon R is equals to I square R. 1 watt is the electric power consumed when a current of 1 ampere flows through a circuit having potential difference of 1 volt. Commercial unit of electrical energy. W is equals to P into T, that is watt second. Watt hour. 1 watt hour is the electrical energy consumed by an electrical appliance of power 1 watt when it is used for 1 hour. 1 watt hour is equals to 1 watt into 1 hour, that is 1 watt is multiplied to 16 to 60 seconds, that is 3600 joule. Thus 1 watt hour is equals to 3600 joule. Kilowatt hour. 1 kilowatt hour is the electrical energy consumed by an electrical appliance of power 1 kilowatt when it is used for 1 hour. 1 kilowatt is 3.6 into 10 to the power 6 joule. Joule's law of heating. Heating effect of current. The amount of heat produced in a wire on passing a current through it depends on the following 3 factors. The amount of current passing through the wire, H, is directly proportional to I square. The resistance of wire, H, is directly proportional to R. The time for which current is passed in the wire, H, is directly proportional to T. Thus, H, heating effect of current, is equals to I square RT.